continue our discussion on biasing of transistor. We were talking about the self bias, in which we have shown that the collector current was independent of the changes in beta, and as I said earlier that a circuit which shows stability against one kind of variation will take care of variations due to other reasons. That means, the cause of variation is immaterial. This circuit is used as a voltage divider also. So, self bias with voltage divider circuit. This has certain advantages, and those advantages also I will point out, but let us first see what is this circuit. Here, this is the voltage divider circuit. In fact, this is the one with the self bias, which is very widely used. This has certain advantages which we will point out. Now, this circuit can be Theveninized. The single resistance R B has been changed with has been replaced by two resistances R 1 and R 2. So, this can be Theveninized, and Theveninized equivalent circuit is this. This is VCC, RC, RE, and this is Theveninized voltage, and this is Theveninized resistance RTH. So, this is Theveninized circuit, which is equivalent of this original circuit. This is actually the design is taken this, but for analysis purposes we Thevenize this, we apply Thevenin's theorem, and we get the value of the Thevenized voltage and Thevenized resistance. Now, Thevenized voltage is, what is the voltage which is observed between this point and the ground? This is Thevenized voltage VTH, and if we complete this circuit here, this is VCC, then we know that this Thevenized voltage will be VTH. This is the current VCC by R1 R2 here. That means, we are discussing this circuit. Here, this is Thevenized voltage VTH, and this is R1 R2, and this is the battery VCC. So, obviously, the current is through this battery VCC by the total resistance, and what will be the voltage developed across this? This is the current into R2. So, this is the Thevenized voltage which we can calculate, and the Thevenized resistance Thevenized resistance, this Thevenized resistance. For finding the resistance between these 2 points, the Thevenin's theorem, as you must have studied, that to calculate the equivalent resistance we have to ground the DC voltage sources. So, this is grounded. So, our circuit becomes this. This becomes the circuit R1 and R2. So, as far as this point and ground is concerned, these two resistances are in parallel. This is grounded, this is grounded. So, this is like this. R1, R2, they are in parallel. So, RTH is equal to R1 R2 by R1 plus R2. So, these are the Thevenized voltage and Thevenized resistances in the circuit, and then that final equation which we wrote for, which showed the high stability, that can be the voltage, because earlier this terminal was connected to VCC. So, that VCC is to be replaced by VTH. So, this is VTH and this is VBE, which for silicon transistor 0.7 volts. So, 0.7 volts divided by RE plus VTH by VRTH, Thevenized resistance, by beta. This is the expression, and now so this is the final expression, and by making RE greater than RTH by beta, we can make the collector current independent of the variations. Independent of beta, that means it is independent of the variations of beta, and this will be highly stable. I said that in self bias, voltage divider circuit is widely used and it has advantages. I talk about two main advantages. Two main advantages of this voltage divider circuit compared with the single resistance RB circuit, and these advantages are that this condition RE resistance should be large, quite large in comparison to this. This condition is better satisfied by Thevenin's circuit, Thevenized circuit. We can see here that when two resistances are in parallel, then the effective resistance is smaller than either. That is the rule of parallel combination. If for example, this is 100 kilo ohm, this is 50 kilo ohm, then the combination will be less than even the smaller resistance. So, RTH, Thevenized equivalent resistance, is less than R1 or R2, and hence when this is low, then this condition can be better satisfied, and so this amounts to better stability. And second point, which is important when we are sourcing our circuit by a battery, because the battery will see the two resistances in series, and hence the output resistance seen by the battery is higher. R1 plus R2 is certainly having higher magnitude than R1 or R2 individually. So, this is, that means it will draw less power. So, the battery life, this is important in the case when our circuit is powered by a battery. So, the battery life will be higher in this case. So, these are the two main advantages for the circuit. Now, I can repeat the design procedure. Design procedure. You see here if these characteristics are available, then we choose the operating point near the middle of the active region, and we already know the value of ICQ, that means quotient current, collector current and voltage drop VCEQ can be read. If these characteristics are not available, as is the often case, then it is safe, because the manufacturer prescribed the value of this IC max. So, it is safe to take ICQ to be equal to half of this IC max. So, this point is known, and VCEQ can be taken as half of VCC, sorry. So, VCQ is known, ICQ is known, and we can use certain whatever we have already studied, that knowledge, that VCC known and IC max this is also known. Then we can get the value of RC. We have to find out the value of RC, R1, R2 and RE in this circuit, and that is the total design. We can assemble the circuit easily. So, RC can be found out from VCC by IC max. So, now RC is also known, and we remember that if we substitute, if we use the Kirchhoff's voltage law, we apply this to the collector circuit, then we get this equation, summation of voltages VCC, here IC is flowing. So, there is a voltage drop here, this is plus minus VCE, and this is RE through which current IE is flowing, and IE and IC are same. So, same current is almost flowing, and so this is equal to IC RC plus VCE plus IE RE, but this is equal to, almost equal to IC. So, this equation then becomes VCC IC RC plus RE and plus VCE. Now, VCE is VCEQ, IC is ICQ. So, VCC is ICQ RC RE plus VCEQ. This is known, this is known, this is known, this is known. So, except RE, all other parameters are known. So, we can find out RE. So, in this series RE is also now known. We have calculated its value. So, the RC is known, RE is known, and the two resistances have to be calculated, and for that we make use of this IE, which is same as ICQ, and this is equal to VTH minus 7 by RE. This is the expression which we have talked about earlier. Now, here this is known, this is known. So, we can calculate the value of VTH. VTH is now known, its magnitude is known, and once we know this, then VTH is equal to, I have just written the expression, is equal to R2 R1 plus R2 into VCC. So, this is known, this is known. Now, one thing, one practice is very common in the design of electronic circuits, that we can assume one of the values R1, for example, we can assume as 3K, 6K or 10K or 20K, and the other can be calculated. This is one way. Otherwise, if we do not want to use our judgment, we can calculate by using the stability factor. Stability factor for a good circuit may be assumed as say 10, and this will give one relationship of R1 and R2. So, we will have two relations, one is here and the other will come from a stability factor, and by using these two expressions, the values of R1 and R2 can be calculated independently, and this way the design is complete. All the parameters of the circuit are known. So, this was about the self bias, and in spite of the fact that this voltage divider arrangement of the self bias makes use one additional resistance, but these two advantages are significant, hence this is most widely used circuit. And now we move to the another biasing scheme, and that is emitter bias. Emitter bias. As I said in the beginning, emitter bias shows stability as high as the self bias circuit, but it makes use of dual power supply, needs dual power supply. And I have explained the meaning of dual power supply, and that is two voltages with respect to ground. One is plus VCC, other is minus VEE. This power supply is needed to implement emitter bias, and then the circuit is simple, and actually this is a very popular biasing scheme operational amplifier, we will go in details later, is one of the most important development in electronics. Today it is hard to find any circuit, analog or digital, which does not make use of operational amplifier. So, operational amplifiers are very widely used, and operational amplifiers usually make use of this biasing scheme, because it is very simple and stability is as good as the self bias case. Now, the circuit is this. RC, RE, and this is connected to this point, minus EE, and this is connected from here plus VCC, and then this is RB. So, this voltage as usual is VCE, and collector current flows here, and here is the emitter current, and from here flows what is IB. This is the circuit, and we can show here that how stability will be achieved. Let us apply Kirchhoff's voltage law to the input circuit. And that will give IB RB, this voltage is VBE. So, plus VBE, and then the drop here, this voltage drop. So, plus IE RE, and this is equal to this voltage VEE. This is minus sign, so it will come minus VE we have taken on this side, and from this we can write IE IB, the base current, is equal to VEE, the magnitude VE, and minus IE RE divided by RB. This voltage is very small in comparison to this voltage. These two voltages may be equal, which are normally used like that, but there is not necessary condition. These two voltages may differ also, one may be 12 volts, other can be 9. So, but normally as I said that equal magnitudes of VCC and VEE are used. Now, from here if we neglect this voltage which is small, then IB becomes equal to almost equal to VEE minus IE RE by RB. Now, for any reason IE is almost equal to IC, and this shows, this is the equation which shows the stability, that if this rises, current, collector current rises, this parameter will acquire higher magnitude and this term will fall. As a result, IB will fall, and this fall in IB will take care of the rise in the rise of this current, because again the output characteristics, if you look, if IB falls, the corresponding IC also falls. So, this is that stability, and using I B equal to I C by beta and V B E equal to 0.7 volts. This I C can be written as and if we design the circuit such that this R E is large in comparison to R beta by B. By this very large we mean, for example, R E is taken 20 times of this factor. This is good enough. If this condition is met, then this I C will be very closely equal to this. We can drop this term, and this shows stability achieved through any variations in the value of beta, because final current, the collector current, is irrespective of this value beta. So, this shows that it is highly stable circuit, design is simple, number of resistances used is smaller and high stability. So, this is very widely used biasing scheme for BJT circuits. Now, the only point is that it needs dual power supply. So, which is of course easily available, and so when dual power supply is available, we can use this circuit. Then the last scheme is collector feedback bias. Collector feedback bias. You see, we earlier had this circuit, this circuit. This was fixed bias circuit. We make a small modification that the terminal is not returned to battery, but we connect here, then the circuit becomes this. RB, RC and VCC. This is the collector feedback circuit. Collector feedback circuit. It is a small change, just we have moved this point to the other part of the resistance RC, and this provides a stability to the circuit. Why? Because here the IB this was simply IB was simply VCC divided by RB. This voltage is 0.7 volts, and this is all fixed. So, this is fixed bias and it is never used with bipolar transistors. this is here this voltage between this terminal and ground, that will control the current I B, and this is variable. We can see if we apply the Kirchhoff's voltage law, to the collector circuit, then we simply get, this is I C here. So, V C C summation of voltages is equal to I C R C plus V C, or we can write that V C is equal to, from this equation, V C is equal to V C C minus I C R C. Now, this is the equation which can explain that how stability will be achieved by the collector feedback. And look at here, for any reason if I C rises, so this term will fall and V C will go down, and this V C in this circuit will send a smaller current, base current, and that will take care of the rise in collector current. It will check the rise in the collector current, and this way the stability will be achieved. Now, so this voltage compensates for the rise in current, and this compensation may not be 100%. And that is the reason it was said that it is much better circuit as compared to the fixed bias. Fixed bias is never used. This is much better circuit, but the stability is good enough for many applications. And this is widely used circuit, because very simple to design, makes use of fewer resistances, just 2 resistances, and in the case of the voltage divider circuit, there were 4 resistors required. So, the number is reduced to half when we talk of a system in which several stages of these circuits are there, then the reduction of resistances is significant to reduce the cost of the circuit. So, that is very important point. Now, if very high stability is not the requirement, which is true for many applications, then this collector feedback bias can be used to achieve the stability. And we can talk a little bit more about the design procedures. We apply the KVL, the Kirchhoff's voltage law, at the input circuit, which gives the I draw the circuit, this is the circuit. I B and when we apply the Kirchhoff's summation of voltages, this voltage is plus minus VBE. So, then we will get Vc, this voltage Vc equal to Vc IB into RB. Vc is equal to IB into RB plus VBE, and using the relation IB is equal to IC by beta, we get from here Vc is equal to IC by beta RB plus VBE. Earlier, this is one equation, let us call it Y, and earlier we obtained a equation Vc equal to Vcc minus IC RC. Let us call this X, and we can eliminate this Vc, because Vc is not known, it is unknown quantity. So, this is to be eliminated, and we eliminate from here, we get from equations X and Y, we get IC equal to Vcc minus VE RC plus so if we can take care of this condition RC to be high compared to RB by beta, then this will show high stability. This term can be dropped, may be dropped, and IC will become equal to Vcc VE divided by RC, and beta is very high, beta is 100, 200 easily. So, this condition is very easy to fulfill, and so this way we have made the collector current totally independent of the variation of beta, and hence stable circuit. As I said that this shows stability, the design is very simple, makes use of fewer resistances, and hence it is widely used. We can go for simple design procedures for this, and we arrive at a very simple relation, simple design procedure. We know from the load line or from the that maximum current IC this is equal to Vcc by RC, and this either from the graph we can take from the where the load line cuts the y axis, or we can use this procedure which is quite safe to take as half of IC max given by the manufacturer in the manual. So, this will be equal to Vcc by, just we substitute here IC max. So, this is 2 RC. This is one equation, let us call x 1 and the equation which we have talked here, this equation, that is, if we neglect this small voltage, then this equation becomes I c is V c c by R c plus R b by beta, let us call x 2. Then from these equations we can simply substitute for I c this value. So, this will be V c c 2 R c equal to V c c R c plus R b by beta. This is equating, this we have obtained by equating equations x 1 and x 2, and here this goes and we simply get a relationship that it gives R b equal to beta R c. This is the simple thumb rule for the calculation of the value of R b. Only there are two resistances, the R c and R b, and one is known from that maximum current relationship, other is known from here. So, the design of this collector feedback circuit is also very simple. I just take as an example that if this is the circuit, if the beta of this transistor comes out to be suppose 80, then we can very easily find out the value of this resistance R b, and so the circuit will be this is 5 kilo ohms and this R b from this relation R b is equal to beta into R c, and this is 80 into 5 k, so for 400 k. So, this resistance is 400 k. So, this way, and this will give the midpoint operation for the collector feedback bias, because in this condition we have used I c is equal to half I c max. This is for midpoint, because here this is I c max point and the half of it is somewhere in the middle. So, we are talking about the Q point in the somewhere in the middle of the active region. So, this is very simple, and as I said, very widely used if extremely high stability is not required. So, that finishes this unit 2 on transistors and the biasing circuit design, circuits, the stability and the design of biasing circuits. I summarize some of the features. We started with the transistors, the NPN and PNP. For normal operation, NPN and PNP work the same way. There is no preference, but as from this discussion you must have gathered that in NPN electron movement from emitter to collector is that takes the whole working of the transistor and transistor action. So, and in the PNP the role is taken by the hole. Electron mobility is higher as compared to hole mobility. So, a NPN transistor will perform satisfactorily, will continue to perform satisfactorily up to higher frequency ranges. And then we discussed the design of the transistor, that the emitter region is most heavily doped, base region is lightest doped, and collector is moderately doped. And then from where we have come to the conclusion of these ranges, this we discussed even in terms of what we call what makes a efficient transistor, that emitter efficiency, collector efficiency and so on, and base transport factor we discussed, and we come out with the same conclusion. The important thing was, and in that the transistor can be biased such that both junctions can be forward biased. That means, we are in the saturation region of the characteristics, and in saturation region the output current and input current, both currents are high, but they are independent, which is against the requirement for an amplifier. And we can make both transistors reverse bias. That is the case again where the two currents are feeble in the emitter circuit and collector circuit, but the two currents are independent. Even if we switch off the emitter current, the reverse saturation current in the collector circuit continues to flow, and that is not what we require in a amplifying circuit. So, these two states are widely used when we use the transistor as a switch, that means in digital electronics. Here the transistor we are using as an amplifier. So, the requirement is, which is very fundamental, that emitter junction has to be forward bias, the collector junction has to be reverse bias. Whether now the transistor can be used in three different configurations: the common base, the common emitter and common collector. Common base circuit is fundamental and is very useful when we talk about the theory of transistor. Transistor action was explained through the common base circuit, and what is the transistor action, that and from where the name transistor came, transistor, trans register, that we transfer the almost the same amount I e to the collector. So, from emitter resistance is forward biased and the resistance is few tens of ohms, to a high resistance circuit, collector circuit, which has resistance of the order of several hundred to few megohms. And this transfer is not possible by simple arrangements of resistances and capacitors. This is possible through an active device, which is transistor, and this is known as transistor action. So, transistor action is transferring a certain amount of current from low impedance circuit to the high impedance circuit, and here. So, this is the active region of the characteristics. There we have seen that the collector current totally depends on the input current, which is I b in a common emitter circuit. And then we talked about the three circuits we will be talking in the next unit, three amplifiers. the common base, common emitter and common collector. But let me mention here that common base is rarely used in practice. The reason is its very low input impedance. If a battery is connected, then low impedance means it will draw high current from the battery. So, the battery life will be extremely poor. There are other reasons. There is no current gain. Alpha is the current gain in common base circuit, and alpha is actually less than 1. The output current versus input current. So, alpha is IC divided by IE, and IC is always less than IE, but close to that. So, alpha is the current gain which is close to 1, but less than 1, hence there is no current gain. But beta, which is the current gain in common emitter circuit, and that common emitter circuit, the input is base current IB and output is collector current. So, beta is IC by IB, and which is very high, and transistors with current gain 50, 80, 100, 200, 300 are commonly available in the market. So, this was about the transistors, and then we talked about the biasing, which is the very important part of the transistor circuits. So, a amplifier will require the emitter junction to be forward biased, collector junction to be reverse biased, and besides that, that will just saying this, that emitter is forward biased and collector is reverse biased is not sufficient. That requires a proper choice of the operating point. By choosing a operating point, we mean choosing DC collector current and DC drop across the junction VCE. So, that is the proper choice of the operating point. Operating point may shift because of 3 basic reasons: temperature, aging, replacement of the device. So, we have to design a good circuit, a stable circuit. So, even if the parameters change, temperature changes or the device has worked for long life, so even then the Q should not vary, and we had discussed the 3 schemes: the self bias scheme, the emitter bias and the collector feedback bias, and these 3 schemes are widely used to design circuits. Depending on our requirements and facility available, any one of the 3 schemes can be picked up and a amplifier circuit can be designed. And so, that we discussed. We will continue our discussion further, and now we will move to the unit 3.